So in our feature selection and extraction phase, we focused on identifying which variables from the BRFSS dataset were most relevant for predicting diabetes. We first reviewed the codebook and manually selected features linked to the metabolic health and lifestyle. After that, removing missing and invalid data, we retained 122 features using correlation analysis and chi-squares tests. We further narrowed this down to 78 key predictors with strong relationships to diabetes status. We then encoded categorical variables with one hot and ordinal encoding and standardized continuous ones. Finally, we using L1 regularized logistic regression. We reduced the feature space to 162 informative variables, achieving a validation accuracy of about 83.6%. The finalized dataset, one for modeling and one for visualization, are stored under the results folder. So next, Saneeya will walk through on how we visualized these findings.
Okay, let's move on to the visualization section of our project, where we explore patterns in the BRFSS 2024 dataset and assess the effects of data cleaning. Figures 1 through 3 focus on data cleaning and data quality improvement. Figure 1 shows the distribution of diabetes responses, where 83% of the respondents reported not being diagnosed, 14.5% were diabetic, and 2.5% were pre-diabetic. Figures 2 and 3 demonstrate how cleaning improved data reliability. The red heat map on the left shows strong correlation of missing data, while the green one after cleaning shows independence among variables. Correspondingly, valid responses increased from roughly half to nearly 90% after pre-processing. The fourth figure illustrates data dimensionality reduction. Here we went from 301 variables to 79 after filtering out redundant or low-quality features, simplifying the dataset for clearer and more efficient analysis. Figures 5 and 6 explore demographic, lifestyle, and health behavior factors by diabetes status. Figure 5 examines demographic variables like age, race, education, income, and employment, showing that diabetes prevalence rises with age and is more common among groups with lower education and income. Figure 6 extends this to behavioral and health factors, including BMI, smoking, physical activity, mental health, etc., where diabetic individuals tend to have higher BMI, lower activity, and poor overall health outcomes. Finally, Figure 7 brings these findings together in a radar chart comparing overall health and behavioral profiles of pre-diabetic and diabetic groups. We see that diabetic respondents consistently show higher BMI and heart disease prevalence, and lower physical activity align with known diabetes risk patterns. Together, these visualizations highlight how systematic cleaning improved data quality and reveal how demographic and behavioral factors collectively shape diabetes risk across the US population. Now over to Prem for the modeling section.
So moving on to the modeling plan of our dataset, the modeling strategy was to compare a broad range of supervised machine learning models and identify which would predict diabetes outcomes effectively. The 4 baseline models that we chose include multinomial logistic regression, naive Bayes classifier, k-nearest neighbors, and decision trees. Each model was trained on the same dataset, split and evaluated using consistent metrics. From the table, we observe that naive Bayes achieved an accuracy of 69%, but struggled with complex feature relationships and showed bias towards the majority class. Decision tree improved the accuracy to 0.75, but tended to overfit our training data. In terms of KNN, we tried 2 variants, one using the Euclidean distance and the second using the Manhattan distance, which achieved a strong accuracy of 0.83%, however, failed to detect the minority classes and revealing an overall class imbalance problem. Logistic regression performed the best among all of our baseline models with an accuracy of 83.6 and the lowest log loss of 0.43. However, it still suffered from the same class imbalance problem. So across all of our models, we observed a clear challenge, which is the dominance of the non-diabetic class and the limited detection of diabetic and borderline diabetic cases. To address this, we plan to handle the class imbalance through oversampling and undersampling techniques. Moving forward, we'll be moving on to some advanced models such as support vector machines, random forest, and gradient boosting models such as XGBoost, which would have the ability to handle imbalanced data sets as well as capture higher order feature interactions. This was the work conducted for our midterm report, and we plan to move forward with advanced models as well as advanced visualizations for the final report. Thank you so much.